Welcome to this presentation of Algoryx Momentum. This is a motion dynamics simulation tool for mechanical engineers. And my name is Peter Norland. I am product manager at Algoryx Simulation and responsible for this software. So let me start out by asking you a rhetorical question. How do you feel about making really nasty and embarrassing engineering mistakes? Not that good, right? But if you ask our users, you tend to get a bit of a special answer to that question. Because to them, making mistakes is a perfectly natural and even invaluable part of the engineering process. And they can make all their mistakes without having costs associated to that. And that drastically changes their mindset about things and ultimately makes them much more agile, confident, and in my opinion, much more brilliant in their engineering work. And I was quite intrigued by hearing their stories about this, and I decided to try this out for myself. And I'm going to show you how, an example of that in just a moment. But first, I want us to have just a little closer look at the particular simulation that we're watching right here. So obviously, this is a system pulling a chain, and we'll see in a second here how the system is jamming because the chain doesn't leave the wheel the way it's supposed to. And it's because as this link starts to fold outwards, it also pulls on the adjacent link here, and that locks it in that position, and it can no longer leave the wheel. So this is an example of a problem that is quite difficult to spot unless you're able to run simulations of this type. And I should also mention that there's no special chain simulation module or anything like that being used in this particular simulation. This is just the multi-body mechanics of Algoryx Momentum. So let's continue. Again, I wanted to try this workflow to see how being open to making mistakes in my engineering process, how that would help me forward, how that would give me valuable insights and direction in my working process. So I decided to invent something. I decided to invent a pill dispenser. And I have no prior knowledge or experience of this type of device. I was really starting from scratch. I even looked around quite a lot on the internet, trying to find examples of this type of device, but I couldn't really find anything useful in that sense. I also gave myself a quite short time span to work on this problem. I gave myself 2 working days to try and develop a good conceptual solution for this problem. And I started with this very simple approach. So a container filled with pills, and underneath it I placed a slider, like so. And at this point I was completely convinced that this wouldn't just magically work, and it didn't. But it didn't cost me anything to set up this simulation. It was a fairly straightforward and quick thing to do. And I was sure that it would give me some good insights about how this type of problem system works. And it did, and it inspired, that information that I gained inspired a next step in this problem-solving process. So it looks like this. We have a slider that runs back and forth, and on the left-hand side we have a push-button mechanism that is designed in such a way that it it prevents the pills from being damaged in this process. It sets a limit as to how hard you can push against the pills if they get stuck in the wrong place like that. And it happens all the time at this stage in the process, and clearly this is a bit of an engineering blunder. I definitely regard it as an engineering mistake. But again, it doesn't cost me anything, and by studying this example, I develop my understanding of this problem, and it becomes a very deep and thorough, natural understanding that is truly invaluable in solving difficult challenges like this. And it led me to a next iteration in the process, and this next step is quite different. So I realized that I can transform this really quite difficult three-dimensional problem into a much simpler two-dimensional problem by allowing the pills to fall down into this narrow slot. And I was really pleased about that. I pressed the simulate button and watched the results. And to my disappointment, this solution does have some issues. It doesn't. You could probably make it work in some sense, but it doesn't work reliably. The pills, they don't really want to fall down into that narrow opening very easily. They tend to like interlock with each other and form almost like an integral structure of themselves. So I need to come up with something that is fundamentally better and more robust. So I started experimenting with the design, modifying the geometry, just playing around with it. And there's one thing to watch a recorded video of a mechanical system, whether it's a simulation or an actual physical system. And it's a completely different thing to be able to edit the design, edit the system, press simulate, and immediately see how that system responds. That gives you a much deeper understanding of how it works. And when you have access to this tool, you can very easily share that understanding with your colleagues, for example. So we have a number of customers that are developing innovative solutions as a team, and then they gather around the simulations and experiment with them, and this triggers this really powerful evolutionary problem-solving process that is a wonderful thing to see. And also just having access to this tool drastically changes your mindset and your ambition as an engineer. So it really has a massive impact in that sense. Anyhow, we still have this problem of the pills not wanting to fall down into that narrow gap very reliably. And I managed to come up with a pretty good solution to that problem. Principle where we have this plane that is slanting just a little bit down towards the opening down here. And this is also surrounded by these three vertical walls. And as a result, we have eliminated virtually all external forces on the system, except for the vertical pull of gravity. So we have effectively removed the circumstances that made it possible for this phenomena to occur, where the pills lock onto one another. So instead, they just slide gently down that slope and fall into the gap. And it's a very, very reliable process. Also note that this design is still very, very simplistic. It is minimalistic and to the point. And that's exactly the type of solutions that people tend to achieve when they use this software. From here, I continued and made some modifications to this sluice part of the system. And that was a really fun process, actually, until I got it to work to my satisfaction. And then I'd spent my 2 days working on this problem, and I'd been able to achieve a conceptual solution that I felt quite pleased with. I'd also gathered a series of videos and simulation models that I can use to illustrate the workings of this system to any person I like. Okay, I have also prepared a short little live demo for you so that you can watch this software run simulations as I speak. We're now in Algoryx Momentum, which is an add-in for ANSYS Space Claim. And we are looking at a model that was originally created in SolidWorks and has now been imported into ANSYS Space Claim. And for those of you who are familiar with ANSYS Space Claim, you know that you can import CAD assemblies from virtually all known 3D CAD formats and edit those geometries directly in this environment. And those formats also include step and parasolid files, for example. And you can edit those as well using the direct modeling capabilities of ANSYS Space Claim. So that is really, really powerful in and of itself. And obviously you can create your own geometries as well. But that creates this really nice setting and environment for Algoryx Momentum. So you can modify your geometries, run your simulations, and really get to know your design. What I want to do here is to perform a number of lifting sequences using this table and investigate what internal loads occur in the system. And before I start, I want to just take a brief moment to think about how we would go about doing this if we didn't have access to Algoryx Momentum. And I would argue that the most common approach would be to assume that the system is quasi-static, meaning that there are no transient effects occurring in the system. And as we'll see later on when we run the simulations, that is quite far from the truth. There's quite a lot of oscillations and dynamic effects, transient effects occurring as these simulations unfold. We also have these features both up here and down here. We can call them rollers, and they have the ability to move back and forth between these tracks, and that happens as this motion progresses. And it is in the motion, the up and downwards motion is in response to mechanical impacts that occur in the system. There are also redundant constraints in this model, and that is something that is notoriously difficult to deal with in simulations and calculations, even though it's something that's always present in the real world. So you can capture that very, very conveniently in this software as well. And so we want to lift something. We want to place some kind of object on top of this table. And you probably want to experiment with different placements of that object. And that is also something that is quite difficult to do, quite easy to do in this tool, and we'll look at that in a minute. Now, let's activate Algoryx Momentum. By default, all of the bodies in this structure are they're fused into one block of rigid bodies. So if we press simulate here, that structure will just fall downwards like that. So in order to do something more interesting with our simulation, we first have to split the structure into independent bodies, like that. So now we have a structure of this type, and then we can proceed and to define our intent with the simulation by for example, merging some of these bodies together again. These wheels and components, I'm not interested in their mechanical behavior and how they interact with the rest of the structure, so I'm just going to merge them with that bottom frame. And by doing that, I have eliminated a set of degrees of freedoms from the simulation, so that increases the performance of the simulation. In this particular case, because this is such a simple, a small model, you're not really going to notice the performance effects of that. But in general, it's a good thing to do for that reason. Also, it simplifies the simulation structure, because here we have this entire block of bodies that are now grouped under one rigid body like that. So it simplifies the working process. And quite a few of our users, they develop and analyze really, really complex mechanical systems that may consist of hundreds of bodies and lots of constraints. So we've designed a specific workflow that is really efficient for doing this process of organizing the structure in those really demanding applications. Next, we want to create some joints, some constraints. And this model, for example, we want to create a constraint here that can drive the motion of the table. And we can do this in a couple of different ways. One is to do it manually by selecting whichever constraint you want to use, or you can do it automatically by clicking Detect Joints. And if I click that button, the software will search the entire assembly and look for places where we have a pin that runs through a hole. And then the software will suggest that as a place where you might want to create a joint. So we get this list of suggestions. And here I'm just going to select them all, and then I can choose between a set of different types of joints. So here I'm just going to choose hinge joints. They have one primary degree of freedom, and that is rotation. So I click that button, and now we have a set of joints in our system. But if we look more closely at it, we'll see that there are a number of places where we actually want to add constraints, but the software didn't do it for us. And here, for example, there's no pin running through this hole, so the model is missing that. It's not giving that cue to the software, so we have to create that ourselves. And again, I'm going to use hinge joints. So I form a hinge joint between this body and this one based on this geometric reference. Here, there are some more pieces missing, so it's hard even for me to really know how this is supposed to work. But for simplicity, I'm just creating a hinge joint there. And then we want to connect that body with that one there and there. Let's stop here for a moment and look at this more closely. So we have two bodies, one that is colored a little more yellowish and one that's a little more orange. I hope you can see that on your screens. And we have these two bodies are connected by two hinge joints, and they happen to be placed along the same line. And this is this makes it a redundant, an overdetermined system. We have redundant constraints here, and this is something that is forbidden in all the software that I've come across, except for Algoryx Momentum. all like multi-body dynamics software. But it is a completely essential part in real practical engineering. I mean, if you look around you, almost all of the mechanical systems that you can find actively utilize and critically depend on redundant constraints in order to function at all. So it is a very important thing to take into consideration, and that is something that Algoryx Momentum has unique capabilities in that regard. So it allows you to, for example, look at the dynamic effects of these overconstrained systems. You can investigate how loads are distributed between different constraints. You can look at the risk of your design jamming in a sense. You can even change the location of your constraints to model deviations or variations in your manufacturing process, so manufacturing tolerances. And this kind of aspect, this situation can cause virtually unlimited loads, internal loads inside of your system. So that is something that can be a really good thing to keep an eye on and investigate thoroughly. And the way we do this is quite simple. We're just adding more of reality into our simulation. So again, this is a hinge joint. So one primary degree of freedom, it is the rotation. But we also include the remaining 5 degrees of freedom. So 3 translational degrees of freedom and 2 rotational. So we're incorporating Hooke's law in this sense. And that's what you'll find as the typical situation in reality as well. And if you have detailed information about the real constraints that you're going to use in your actual physical product, then you can enter that information into your simulations and investigate the effects. Let's continue. We still have a few constraints missing. I'll just create them a little quickly. Here we're missing some constraints as well, so we'll add those there, tying up this structure even more. Like so. Now, why don't we try and simulate the system and see what happens. It just drops down like that again, and it's because nothing in this model is attached to the world coordinate system. So let's attach the lower frame to the world by turning it into a static body. Simulate again, and the whole thing, the table drops down like that. It's exactly what I was hoping for. And these orange markers, I hope you can see them, they indicate contacts. And Algoryx Momentum handles contacts completely automatically, and the mechanics reflect the actual design, the actual shape, 3-dimensional shape of the bodies in the structure. That is another unique feature of this tool. Let's look at the simulation again. We see that there are some things missing here. We need to create another constraint here between these two bodies. Like that and like that. Good. Press simulate again. And now we see that the table is locked. It doesn't drop down. And it is because this joint right here, we defined it as a hinge joint. So it doesn't permit a linear motion. So we have to change it into a different type of constraint. So I've selected it now, and I'm looking at the properties of this joint. And I can click here to list different options. So I could turn it into a prismatic joint, which allows a linear motion only, and that might be, you know, the perhaps an intuitive, a natural choice. But if you think about how a cylindrical, a hydraulic cylinder actually works, you'll find that it does allow also rotation. So that is part of the way the system works. So you really shouldn't lock the rotational degree of freedom. Instead, you should use a cylindrical joint. And this is something that we find with quite a few new Algoryx Momentum users, that they, especially if they've used with other multi-body dynamic simulation tools before, that they tend to opt for simplified descriptions of realities. Reality. They want to eliminate as many degrees of freedom as possible. But with this tool, you should do the opposite, because here you can handle all of the redundant constraints of your real design. So you bring in more of reality in your simulations. And that, in turn, suggests that you should be more careful with how you set it up. You should pay more attention to how it actually works, so you don't add constraints that are not part of your real system. So there, now turned it into a cylindrical constraint. And we simulate, and the table falls down. Very good. Here is something that I'm not quite pleased about. See that bar lands on top of the hydraulic cylinder. Let's look a little more carefully at that. So let's just pull out this cross-section view. We can also watch the playback in slow motion. Now keep an eye on that beam. It lands directly on top of the hydraulic cylinder, and I don't think that's a very good thing. I would have preferred to have a more intentional mechanical stop in this design. And so, I mean, in effect, we have discovered an engineering mistake right there, without even looking for it. Okay, so just for our purposes today, I'm going to utilize the some features of that cylindrical joint in order to limit the motion. So we're looking at the properties of the cylindrical joint, and it does include a quite big range of different features and parameters, so that you can define that joint the way you want it to work. But now we just want to define a linear range for this motion, and I'm setting the limit to -3 centimeters. I'm using metric units here because I'm Swedish. Press simulate, and there we have a clearance. Perfect. And as I mentioned before, I want to perform a series of lifting sequences with this table. So let's do that. And I want to start from the lower position. So I'm just playing forward until a point in time where I want to proceed my my analysis. We can look at it from here, from this vantage point as well. Keep an eye on what's going on right there. Okay, but let's say that we want to run our next subsequent studies from this starting position. I just click New Initial State, and next time I press Simulate, the simulation will start from this new position. Let me just go back to real-time playback, like so. And we can see how these things, they're still flopping around like that because they remember the motion from the previous simulation. And obviously, if you want to, you can go in and modify all these initial velocities to whatever initial state you want. All right, so let's start defining this upward lifting motion. Again, we're using the hydraulic cylinder, and then this time I'm activating the linear motor. I'm setting a target speed, and then I'm allocating force limits, and then the constraint or joint can use this amount of force in its attempt to achieve that target speed. It is lifting the table. Very good. Now, let's use some rudimentary direct modeling features of space claim in order to create an object on top of this table so that we can perform our lifting sequences. So let's place it there to begin with. Extrude it a bit. Add it to the simulation model. Go back to Algoryx Momentum and simulate. We see that this box is immediately interacting with the table through automatic contacts. We can look a little more closely at these rollers to see what's going on there. So now we're watching this in slow motion, and in the initial position here, the rollers are being pushed up against the upper limit, and press simulate. We see that it bounces up and down a little bit, and then eventually drops down to the lower track, and it also bounces when the hydraulic cylinder reaches its the end of its range, and which causes a mechanical impact that runs through the system. We can grab this body, and move it to any place we like for the next simulation. But let's also have a look at one of these constraints to see what loads it is subjected to during this sequence. So I've now added it to the plot tool, and here we can specify what set of data we want to have represented on the x-axis and the y-axis. So let's, on the y-axis, just select the force magnitude, and on the x-axis we can choose between any set of output data belonging to any object, whether a body or constraint, in the simulation. But for simplicity now, I'm just choosing time as a parameter there. Now we can grab this panel over there so we can see the simulation and the plot side by side. Press simulate and the software starts generating the data. And as you can tell, there's plenty of transient effects going on with this particular setup of the system. I can move this box yet again to a new position. Press simulate and study the new results. So yet again, we're discovering a bit of a problem with this design. Apparently it's not entirely safe. Let's look at it from over here to get a really good idea of what's happening here. So clearly we need to add an additional limit to that to the tracks in the on the table side. And again, this is direct modeling, so I can edit my geometries however I want to, very conveniently, and the simulations understand the new geometry directly. So this really, it is an environment where the actual design gets to speak very much for itself, and that helps the engineer to detect potential problems and also opportunities with the design, things that the engineer wasn't perhaps actively looking for. So that is a really valuable component of what you achieve with this software. Okay, there are many more things to say about Algoryx Momentum, but I think I'll leave it at that for now and go back to the main presentation. Okay, I want to thank you all for attending, and I hope that you'll all take the time to try the software for yourself, because it's proven to be a real game changer for many engineering departments around the world. So you can use this link. It is also available in the YouTube description, so you can just click on it there and request a trial license. With that, thank you again, and have a good day.